Welcome to session 3. Today in this session we are going to study about another mode of heat transfer, which is convection. Convection is the process of transferring heat by actual motion of heated material. Like convection is of two types, natural or free convection, and another type is forced convection. Let me remind you with the definition again. Convection is the process of transferring heat by actual motion of heated material. Let's try to understand what is natural or free convection. It is the motion of heated materials caused by density differences. Let us try to understand this by an example. When a vessel filled with water is kept on heater, then, due to the conduction, the water at the bottom of the vessel gets heated. Consequently, the density of heated water decreases and thus moves upwards. Hence, heat from the bottom of the vessel transfers to the top by actual movement. Let us try to figure out this by an picture. This picture tells the same story. Here, a vessel filled with water is kept on a heater, where heater is continuously providing heat to the vessel. Thereby, the water is getting heated by the vessel through the method of conduction. Further, the heated water is getting upwards, like the bubbles located in this area, that is at the bottom of the vessels, are getting heated through the vessel through the theory of heat transfer of conduction. As they get heated, their density decreases. Thereby, it allows them to move upwards, and thereby, while they are moving upward, they carry the heat with them and thus cause the heat transfer on the other water particles through convection. This theory happens due to the change in difference of densities. Therefore, it is called as natural or free convection. The next type of convection we are going to study is forced convection. The process of forced convection is when a blower or pump forces heated material to move. In the natural or free convection, the material automatically moves itself due to the difference of density. But in the forced convection, that heated material has been given an external power of blower or pump to make it move. Examples of forced convection are when a hot air blower is switched on, the air gets heated by any heating element and the heated air is blown by the fan. Thus, the heat is carried by the air wherever it goes. That means when an air blower is switched on, the air is first gets heated inside the blower. That has been done by a separate heating element. Further, as the air gets heated, that has been blown away by the fan. The blower itself has a fan in it which blows away the heated air. This causes heated air to carry the heat with it to the atmosphere or wherever it goes. The third kind of heat transfer we have studied is radiation. When energy is emitted by a body in space, travels in the space and falls on the other body to increase the thermal energy of receiving body, this is called radiant energy or thermal radiation or radiation. This kind of energy or radiation energy does not require any material medium for heat transfer, as we see that it can travel in space, and when it falls on the other body, it increases the temperature of the other body. The best example for the radiation is heat from the sun that travels millions of kilometers before falling on the earth. Further, the next thing we are going to cover today is electricity. What is electric current? If 1 coulomb of charge passes through an area in 1 second, then the current is 1 ampere, where coulomb is denoted by capital C, time is denoted by unit second, and second has a symbol of small s, and current is denoted by ampere with a symbol capital A. If the charge is positive, then the direction of current will be in the direction of motion. That is, the charge that is passing through an area is positive, then the direction of current would be in the direction of motion of the charge. And if the charge is negative, then the direction of current would be opposite to the direction of motion of the charge. What is current density? The amount of electric current flowing per unit cross-sectional area of the material is called current density. If a current I is uniformly distributed over an area S and is perpendicular to it, then current density can be defined as J is equals to I by S, where I and S have their usual meanings, as we have studied in the previous slide. Let's try to understand this using this example. If a current I is uniformly distributed over an area S, here the current I, here it is uniformly distributed over the area S. This is the area S, and I current is uniformly distributed, and also it is perpendicular to the area. It is actually perpendicular to the area. Therefore, the current density can be written as J is equals to I by S, where J is denoting current density. Further, if phi is the angle between the area and the direction of current, then J can be written as del I divided by del S cos phi. That is, if the cross-sectional area has an angle phi with it, then the formula of current density can be written as J is equals to del I divided by del S cos phi, where phi is the angle of the area that has been maintained between the horizontal axis and the cross-sectional area. Electric current has both direction and magnitude, but as it does not add up using triangle law of vector addition, thus it is not a vector quantity. Electric current density is a vector quantity. This point to be noted that electric current is not a vector quantity, but electric current is a scalar quantity. As the conditions for a quantity to be a vector quantity is the quantity should have both direction and magnitude, but that should also add using the triangle law of vector addition, and the electric current doesn't add up using the triangle law of vector addition. Thereby, it is a scalar quantity. Rather, electric current density is a vector quantity. Exercise time. So, the question says, if an electron beam has an aperture of 2 mm square, around 6 into 10 power 16 electrons pass through perpendicular cross-sectional area per second. Find current and current density. Consider the charge on electrons is equals to 1.6 into 10 power minus 19 coulomb. So, the given conditions are, the aperture of an electron beam is 2 mm square and around 6 into 10 power 16 electrons are passing through the perpendicular cross-sectional area per second. We need to find current and current density, and the charge on the electrons are considered to be 1.6 into 10 power minus 19 coulomb. Therefore, total charge passing through the cross-sectional area Q is equals to number of electrons into charge of electron. Look, we have to find out total charge passing through the cross-sectional area. How much charge will flow from the cross-sectional area? That is charge on one electron multiplied by the number of electrons passing through that cross-sectional area. Here, number of electrons, we are denoting it by small n. Charge of electron has been denoted by small e. Thus, total charge passing through cross-sectional area can be written as Q is equals to n into E. On putting values to these n and E, we get the total charge passing through the cross-sectional area is equals to 9.6 into 10 power minus 3 coulomb. Further, we need to find out the current. Current can be written as I is equals to Q by T. Q is the total charge passing through the area and T is the time. At what time this charge is passing through. Here we have considered time is 1 second as given in the question. Therefore, I is equals to 9.6 into 10 power minus 3 divided by 1. Thus, the current flowing through the area is 9.6 into 10 power minus 3 ampere. As charge is negative, the current will be in opposite to the direction of motion of the beam. The current density is J is equals to IS. As we have learned this formula in the previous slides, current density is denoted by small j, which is equals to I upon S. That is current upon the cross-sectional area. Here, the cross-sectional area is 2 and the current we have calculated is 9.6 into 10 power minus 3 ampere. Therefore, the current density is equals to 4.8 into 10 power minus 3 ampere per meter square. So is the answer of our question. The next topic we are going to cover is electric field inside a conductor. Let's understand this by making cases. In case A, there is no electric field is applied. So, when no electric field is applied, the charge particles will be uniformly distributed in the conductor. In the case 2 or case B, on application of electric field on the conductor. When E is created on the left to the right, it causes electrons to redistribute themselves, where E is the electric field. Therefore, when electric field E is applied from left to right, it causes electrons to redistribute themselves. This drift of electrons causes an internal electric field, E dash, from right to left. We have seen the electric field was applied from left to right, but that caused redistribution of electrons, and that redistribution took place in the opposite direction. That redistribution caused generation of internal electric field, E dash, from right to left, that is opposite to the E. At this point, a steady state of positive and negative charge particles appear on the surface of the plate, where E is equals to E dash. The next thing we are going to cover is drift velocity. So, what is drift velocity? The average velocity attained by a charged particle in a material due to the application of electric field is called drift velocity. If an electron drifts a distance L in a time t, the drift velocity can be defined as Vd is equals to L by t, where Vd was the drift velocity, L is the distance covered by the electron, and t is the time in which it has traveled the distance. When there is no electric field in conductor, the drift velocity is equals to 0. That is Vd is equals to 0. When there is electric field in the conductor, Vd is constant, because as soon as the electric field is applied, the electrons will start to travel in some distance. The direction of drift velocity will be opposite to the field of electric field. The next thing we are going to cover is Ohm's law. Ohm's law states that voltage is directly proportional to the current, where resistance is the proportionality constant and depends on temperature of conductor. This is a very basic circuit to understand the Ohm's law. Let there be a circuit where voltage V is applied, causing and current I to move through the resistance R. Thereby, Ohm's law can be mathematically written as V is equals to IR. As we have seen in the previous slide, Ohm's law states that voltage is directly proportional to current. That is, if higher the current, higher will be the voltage. Lower the current, lower will be the voltage. But the proportionality constant of this equation is R. That is resistance, where resistance is equals to rho L by A. This sign is pronounced as rho. Rho L by A is equals to resistance. Let's try to understand these concepts using exercise. So, the question says, calculate the resistance of a copper wire of length 60 cm and cross-sectional area 2 mm square. Consider the resistivity of wire is equals to 1.72 into 10 power minus 8 ohm meter. Thus, listing out the given conditions first. In the solution, the length of copper wire is given as 60 cm. We can denote it by L. We need to convert that centimeter into meter. We need to know that 1 meter is equals to 100 centimeter. Thereby 60 centimeters is equals to 0.6 meter. The cross-sectional area of the wire A is equals to 2 mm square. When this is converted into meter scale, it can be written as 2 into 10 power minus 6 meter square. The resistivity of wire is considered to be as 1.72 into 10 power minus 8 rho meter. We have denoted resistivity of wire as rho. As we have studied, the resistance of wire R is equals to rho L by A. Therefore, we are going to find out first the resistance of wire. By putting numerical values to this equation of resistance, we can write rho as 1.72 into 10 power minus 8 multiplied by L, that is 0.6 meter, and cross-sectional area A, which is 2 into 10 power minus 6 meter square. On solving this equation, we get the result of resistance of wire is equals to 0.00516 ohms. Now we are going to study about temperature dependence of resistivity. Consider a material of following characteristics. At temperature is equals to T, the resistivity is equals to rho T. At temperature equals to T naught, the resistivity is equals to rho T naught. Let alpha is equals to temperature coefficient of resistivity of material. Given in the table are the resistivities of different material that are generally being used. Here, let the resistivity of silver be 1.47 10 power minus 8. The resistivity of copper is 1.72 into 10 power minus 8. The resistivity of gold is 2.35 into 10 power minus 8. The resistivity of aluminium is 2.63 into 10 power minus 8. The resistivity of tungsten is 5.51 into minus 8, and so on. The unit of resistivity is alpha meter, and here alpha is temperature coefficient of resistivity of material. Then for most materials following can be written: rho T is equals to rho T naught into 1 plus alpha T minus T naught. Change of temperature causes change in length and area of material as well. And we have studied previously that R is equals to rho L by A. And we are saying that change of temperature causes change of length and change of area. So coming back to our slides, we can consider these changes as quite small and are treated as constant. Therefore, resistance would become directly proportional to rho. Hence, this equation can be also written as RT is equals to RT naught into 1 plus alpha T minus T naught. The next topic that we are going to cover is superconductors. What are superconductors? Materials for which the resistivity suddenly becomes zero below a certain temperature are called superconductors. The corresponding temperature is called as critical temperature. Let us find it out using the following graphs. Here, this is the graph of a normal metal. Since the temperature goes down, the resistivity goes down, as we can see, but it never goes to zero. This is the behavior of normal metal, that is resistivity of normal metal. Here, in the another graph, we can see as the temperature goes down, there comes a point where the superconductors believed to have resistivity of zero. The temperature at which they possess this property is called critical temperature, and so these materials are called superconductor. The usage of superconductors can be seen on building construction of strong magnets and manufacturing of ultra-fast computer switches. The next thing we are going to study is battery and EMF. Here we see batteries maintain a potential difference between their terminals. If a charge Q is taken from the terminal B to terminal A, which are distance d apart, then the work done by the battery force is equals to Fb into d. Let's try to understand this again. This is the working principle of battery. There are two terminals here. This is the first terminal. This is the second terminal. What batteries do? Batteries maintain a potential difference between their terminals. If a charge Q is taken from terminal B to terminal A, which are d distance apart. Here we can see a charge Q has been taken from terminal B to terminal A. The distance between the terminal is d. The force acting for taking the charge from B to A is Fb. Then the work done by the battery force is equals to Fb into d. The work done per unit charge can be written as E is equals to work done upon Q. That is, Q is the unit charge. Work done we have already studied in the previous equation, that is equals to Fb into d. Therefore, we can write work done per unit charge is equals to E is equals to Fb into D upon Q. This is called electromotive force of the battery, or in short, it is said as EMF. As observed, EMF is not actually a force, but it is actually called as work done per charge. The points to be noted here are potential difference and EMF are two different quantities. As we saw, there was a potential difference between the terminal B and terminal A, which caused an electron to move from terminal B to terminal A using a force Fb, whereas EMF has been defined in the previous slide as work done per unit charge. EMF, that is electromotive force, are non-electrostatic in nature. The potential difference originates from electrostatic field created by the charges accumulated on terminals of battery. The EMF of the battery is equal to potential difference between its terminals when the terminals are not connected externally. Here we close this session. Thank you.